This is our case study on the Air Force's pilot shortage issue. The members of this group include Meghan, Vandermaas, Anna Leland, and Samantha Shiffman.
Okay, for our outline today, we'll be going over everything that we went over in our actual case study. So that will include the executive summary, background and introduction, framing the decision, developing objectives and measures, generating creative alternatives, assessing alternatives with deterministic analysis, identifying uncertainty and conducting a probabilistic analysis, and then we'll end with our final recommendations based off of everything that we talked about before it.
So as far as the background and information goes, this project will cover an in-depth study to find a solution to fix the United States Air Force's pilot shortage. Recently, it was reported by the Secretary of the Air Force that the Air Force is experiencing a shortage of a little under 2,000 pilots. The shortage is being felt across all positions in the Air Force, whether they're directly involved with flying or in support of the mission. Since the Gulf War, the number of fighter squadrons has decreased from 134 to 55, almost a 60% decrease. This has placed an excessive workload on those left to complete the mission, minimizing the quality which our nation is defended. This project will look at several alternatives to the issue at hand and use various methods to analyze each one. The analysis will help the team determine the optimal solution for the United States Air Force. So some key assumptions that we can make here is that the Air Force is 2,000 pilots short across all branches of aviation. Of those 2,000, 1,300 are fighter pilots, and we see the greatest debt in bomber and mobility fields. The Air Force desires to increase this pilot production by 25%. The Air Force will never, though, be able to match what's going on in the benefits of the civilian sector. There are many options available to ensure superior quality of service and quality of life for our military pilots. So this case study will analyze those. Vision statement, the engineering team will provide the Air Force with an innovative solution to the pilot shortage. Quality, integrity, costs, responsiveness, and timeliness will be emphasized. As far as the issues go, the nation itself isn't producing enough pilots to satisfy the military or the commercial needs. The airlines pay their pilots far more than the Air Force ever will. Many job openings in the civilian sector as the air industry is growing, like RPA pilots are finding more job openings outside of the Air Force because technology is advancing. So this is our decision hierarchy, and the hierarchy describes the possible decisions available for the team to decrease the pilot shortage. The decisions are broken down into four main sections: production, absorption, demand decrease, and sustainment. Production is the idea to increase the number of pilot trainees who become military pilots. Production can be acted out by either increasing the number of pilots accepted through pilot training and diverting experienced pilots to becoming IPs to ensure that teacher numbers are high enough to train the current class effectively. Absorption focuses on increasing the number of pilots who become experienced within the Air Force. Two strategies for implementing this plan are to lower the number of required hours to be considered a senior pilot, or to shorten UPT altogether but replace them as training with a greater number of hours hands-on training in the pilot's intended and final aircraft. Demand decrease is a plan to lower the demand for pilots in both the military and civilian sector, and this would make the shortage less damaging to the Air Force. Sustainment is the final decision available, and this is a plan to keep experienced pilots in the Air Force flying as long as possible within the military instead of transferring to the civilian sector. It can be done by increasing quality of life for pilots. Current choices for this include increasing incentives like monetary values for military pilots, decreasing the number of extra duties that they have to do, increasing the percentage of a pilot's career actually spent flying, as opposed to retiring to more management positions. This is our value hierarchy. It includes decision functions, direct objectives, value measures, value functions, measure explanations, as well as our stakeholder swing weights you can see on the bottom row. So as far as creating alternatives, we focus on production, absorption, and sustainment. Some of the hybrid alternatives that we came up with were like making the job more desirable, so that includes lumping together or decreasing additional duties, time away from home, and offering more incentives. Also, we can increase the number of UPT grads by lowering requirements and granting more medical waivers. Our final alternatives were making the job more desirable, one of our hybrids, decreasing training time, decreasing training difficulty, and offering more pilot slots. Swing weight matrix, and it helped the team properly assess weights by explicitly defining their importance and variation in value. These two charts help to determine first what alternatives dominate the others based on the values that were assigned to each, and second it determines what alternatives dominate based on cost. So we use these two models to determine that decreasing the difficulty of training was the optimal solution.
In order to improve the value of and mitigate the risk of the recommended alternatives, the team decided to model uncertainty with probabilistic analyses. Incorporating risk allowed the team to make a more informed decision on which systems outperform others even when operating under uncertainty. The chart below is a stochastic value component chart with integrated uncertainty into the total score of an alternative. Each alternative is listed on the bottom with baseline and ideal being the options closest to the legend. This chart shows how each alternative compares to the other with uncertainty included, so each alternative can be compared fairly. It can easily be seen that System 3 is the most desirable option in comparison to the ideal option on the far right. The chart below is a tornado diagram with uncertainty. The team assessed Alternative 2, decreased training time. This alternative happened to be on the deterministic Pareto frontier along with Alternative 3, decreased training difficulty, and therefore was a viable choice for best option. The team wanted to assess the uncertainty in all measures for this alternative. One can easily see the MMD, minimized military demand, measure has the greatest amount of uncertainty, so basing an alternative on this measure is the riskiest choice available. Alternatives should instead be compared based on how their other measures are held. The uncertainty of this measure essentially encourages the team to look more critically at alternatives that are heavily based on this measure. The final uncertainty analysis the team built was that of a stochastic Pareto chart shown here. This chart includes uncertainty in each alternative's final normalized score and its price. This chart allows each alternative to be seen in a utility versus cost format and shows which alternative is likely to be most cost-effective, while simultaneously showing the risk of choosing said alternative. This chart shows that even with uncertainty included, System 3 is a dominant solution. Other systems may have a risk allowance that shows they may be a dominant solution, but this team is risk-averse, and System 3 shows the best option with the least amount of risk involved. System 3 is the alternative to decrease training difficulty of pilots.
So last but not least is the final recommendation. We determined throughout all of our analysis that decreasing the difficulty of UPT was the number one alternative. It came out on top compared to all the other alternatives. Decreasing the difficulty of UPT requires an emphasis on training and different learning methods. So we would need to target parts of the program that have the highest rates of failure in order to bring focus and attention on those different parts so that we can revamp those portions to increase the percentage of successful trainees going through pilot training. This would also require an investment in technology, so that could have a little bit to do with the uncertainty of the cost variables associated with this recommendation. However, we think it's number one compared to the other alternatives we came up with.